This is about nonlinear least squares estimator. So we assume that y, the linear regression, it's not linear, it's nonlinear regression plus at a term, and g is a known function. G is known, like that means the only unknown is theta, and x is m-dimensional, theta is included in capital theta and k-dimensional, and mean independence is assumed. Conditional mean independence is assumed. Okay, and then we are going to estimate the theta, the parameter theta, by minimizing this guy. Okay, so this is basically same as the least squares or LS type estimator, just minimizing the residual. Okay, and of course I multiplied 1 over 2 to simplify the algebra later. And I'm going to make these 5 assumptions. So first, if theta is wrong, then there is a positive probability of x. For a positive probability x, y minus wrong theta is different, expectedly different. The expectation is different, right? So later we are going to use this for and compact, and g is twice continuously differentiable, and the second derivative is bounded, and the something is non-singular, which is the full rank assumption. Okay, there are many questions. F is missing, right? Hidden assumption, hidden question. Anyhow, let's go. The first one, theta is the unique minimizer of expected value of L, expected value of L. So that is like L theta is 1 over 2, 1 over 2, y minus gx theta squared. Okay, and I will show that expected value of theta tilde minus expected value of L theta 0 is positive for any theta tilde in the parameter space such that theta tilde is different from theta 0, right? How do we do that? Like, let's see. First, let me try this first. Expected value of L theta 0 is, let me drop 1 over 2, that's not important here, yi minus gxi theta 0 squared. Okay, that can be written as simply u squared, right? And now then li theta tilde is this guy, but I'm going to change y into, split y into g xi theta 0 plus u instead of y minus gx theta tilde squared. Okay, so that's what we get, and then it equals, just expand the square term, then expectation of ui squared plus expectation of g xi theta 0 minus gxi theta tilde squared minus 2 times expectation ui gi theta 0 minus gi theta tilde, right? So it's expansion. And then first, I'm going to show that this equals to 0. That is pretty simple. By law of iterated expectations, you may write that guy, expectation ui gi theta 0 minus gi theta tilde equals expectation of expectation ui gi theta 0 minus gi theta tilde given xi. But as you know, the GIs, these two functions depend only on xi, right? Like the randomness is coming from xi. So you can bring them out of the expectation, and then we get this, and then obviously this is 0, so this will be 0. So the last term will be 0. Then now we have this guy here and this guy here, sorry, right? So, and of course, expectation of u squared will be cancelled out, and as a result, what we get here is expectation of Li theta tilde minus expectation of L theta 0 equals expectation of Gi theta 0 minus Gi theta tilde squared. Okay, we have to show that this is strictly positive. It is from this is from assumption 1. In assumption 1, probability of x such that expectation of y minus Gi theta tilde is not 0 is positive, right? So, right here again, like this means expectation of y means it is expectation of Gi theta 0. This is positive. Okay. So, its square cannot be 0, right? By the Jensen's inequality, right? Because it is this guy is non-zero, so the squared second moment cannot be 0. Okay, that was part A. We have done part A. Now let's do the calculus. B, Li is 1 over 2. Now I'm going to use 1 over 2 again. Yi minus G. I will just write it as Gi theta this way. And then the first derivative is minus Gi theta over theta times Yi minus Gi theta. Right? Simple. So it's and differentiate this guy again. Then if you differentiate with respect to this and this, there will be 2 terms. So let me do this first, the later one first. Then you get okay, I transposed here, so it is a matrix. Minus, now if I differentiate with respect to the first one, formal one, then this is the second order derivative. So I just did the calculus here for the later questions. Let's see the next one. Part C, show that this is non-singular. Okay, I will show that like theta 0. So first, let's calculate what this guy is. So this is, so this is expectation of these guys with theta zeros, okay? And first, I will say this part will be 0 after taking expectations, okay? The reason is pretty simple. Expectation of Yi minus Gi theta 0 is expectation of second derivative times u, and then by the law of iterated expectations, you know, it is expectation of something, the second derivative times, and this is 0 by assumption. So this will disappear, and we have 0 like this. So this is the second order derivative. Usually we call this Jacobian matrix. So like we may want to denote this as Ji times Ji transpose, right? So then by the assumption, like this is non-singular by using the fifth assumption. This implies the C. That replaces the full rank assumption of linear model. Okay. Now show that the second derivative is dominated. D. I would like to show that expectation of sub theta this is bounded, right? And again, we are going to use this functional form to do that. Like I will use the assumption that, so the assumption we need is this one, the fourth assumption and the second assumption, all right? So theta is compact, the set is, the parameter space is compact, and that is bounded. So the reason why I need that here is, so because the second order derivative is bounded, like say, I mean, this is bounded. So let me write it as C, right? The constant is C. It is always strictly smaller than C. Then I say like this will imply, right? And also, excuse me, also because theta is compact, it is bounded. That means for any theta 1 and theta 2 in the set, the distance can be bounded. So it's, let's say, C1, C2, okay? And then intuitively speaking, these two implies this is the slope of the first derivative. So first derivative is also bounded by these two numbers, right? The slope is bounded and the area is also bounded, the distance is bounded. So the function cannot be infinity. So let's say you can just say something, another constant. And because again the slope is bounded, so the original function should be bounded, right? Simply speaking, let me explain this a little more in more detail. So suppose if this is bounded and this is also bounded, then we can say for any theta in the parameter space, we may write it as g theta 0 plus theta bar using linear approximation. Okay, this is a simple Taylor theorem. So then the absolute value is less than this guy plus this times this. So this is obviously finite and this is bounded by C1 and this is bounded by C2. So this is bounded by another constant. So this is just intuition. I just wanted to explain it more clearly. Therefore, that means all the second derivative, boundedness of the second derivative and the compactness of the parameter space implies the first derivative and the original function are also bounded. So then just apply this to the functional form. We are now binding L, not G, okay? And remember, it was this minus second derivative times yi minus gi theta, something like this. Okay, and then I will bound it like say everything will take plus like this. Okay, it's easy. It is an inequality. If you take absolute value, they will become like this. And I will bound it by C3, C3, and it was C1. And still we have something. And so we just need to bound that guy. So yi minus gi theta will be ui plus gi theta 0 minus gi theta. So that is ui plus gi theta 0 minus gi theta. And we learned this guy is bounded by say C3 times C2. Okay, remember it was I will write it this way: ui plus g derivative times theta 0 minus theta. So it is bounded. So everything is bounded. Just the only thing here is this randomness. So if expectation of the absolute value of u is finite, then proof complete. Right? So that's how we bound this thing. Okay, I will stop here and continue in the next video.